Here's something many homeowners don't realize. Heat rises. In homes with inadequate ceiling insulation, that rising heat flows directly out of the house through roof assemblies during winter, representing 25 to 40% of total heating loads in poorly insulated homes. Simply adding enough insulation to ceiling or attic assemblies to reach R60 values can reduce that heat loss by 75 to 90%. The economics of comprehensive ceiling insulation improvement rank among the most favorable of any home improvement investment. A typical 1,500 to 2,500 square foot home can receive complete ceiling insulation upgrade for $1,500 to $3,500 in materials, or $3,000 to $6,000 with professional installation. The annual energy savings typically run $300 to $700 depending on climate severity, heating fuel costs, and baseline insulation levels. The payback period usually runs 4 to 12 years, depending on specific circumstances, with continuing savings accumulating across the insulation's expected 50-plus year operational lifespan. Understanding what R60 means, why ceiling insulation matters so substantially, and how to achieve this insulation level helps homeowners capture energy savings that most American homes are currently missing through inadequate ceiling insulation. The basic physics of ceiling heat loss involves thermal transfer through materials, separating conditioned interior spaces from unconditioned attics or exterior roof assemblies. Heat moves through materials in proportion to temperature differences and inversely proportional to thermal resistance measured in R values. Higher R values mean greater resistance to heat flow. Each additional unit of R value produces proportionally greater thermal resistance across the assembly. Modern building codes typically require R30 to R49 ceiling insulation depending on climate zone, but substantially higher R values produce meaningful additional savings through reduced heat flow. The R60 target represents a practical optimum for most American climates. Moving from R30 to R60 roughly halves the heat loss through ceilings for typical winter conditions. The additional material costs remain modest while capturing substantial energy savings. Pushing beyond R60 toward R80 or R100 produces diminishing returns as marginal savings decrease while material costs continue rising. For most applications, R60 represents the point where cost-effectiveness optimizes balancing investment against ongoing savings across expected insulation lifespans. Jennifer Ballantyne, a home performance specialist who has upgraded ceiling insulation in over 700 homes across the Midwest, has documented typical energy impact patterns across her projects. Her data shows that upgrading from typical R20 to R30 baseline insulation to R60 levels produces average heating cost reductions of 18 to 28%. The specific savings vary with baseline conditions, climate severity, home envelope performance, and heating fuel costs, but consistent substantial benefits appear across her diverse installations. The material options for ceiling insulation provide flexibility matching different application contexts and priorities. Blown cellulose insulation provides excellent thermal performance with low environmental impact and modest cost. Blown fiberglass insulation offers similar thermal performance with somewhat different material characteristics. Spray foam insulation provides maximum air sealing alongside thermal performance at premium cost. Rigid foam boards can supplement other insulation types in specific applications. Batt insulation provides simpler installation in some applications, but requires attention to proper installation for good performance. Each material has appropriate applications based on specific circumstances. The installation approaches for ceiling insulation, upgrades vary based on existing conditions and chosen materials. Blown insulation approaches work well for open attic spaces accessible from above, with installers spreading insulation evenly across the ceiling plane. Dense pack approaches can retrofit insulation into closed ceiling cavities, without opening finishes when access limitations prevent blown applications. Spray foam approaches work well for cathedral ceilings and complex assemblies where blown insulation wouldn't perform adequately. Professional installation offers appropriate expertise and equipment for most applications, though simple blown installations remain feasible for motivated homeowners with rental equipment. Theodore Blackburn, a residential energy auditor specializing in Pacific Northwest climates, has documented specific patterns affecting ceiling insulation effectiveness in various home configurations. His research shows that air sealing at ceiling planes often matters as much as pure insulation thickness for achieving optimal performance. Uncontrolled air leaks through ceiling penetrations for lights, plumbing, HVAC registers, and other penetrations create bypass flows that reduce insulation effectiveness, regardless of installed thickness. Comprehensive improvement projects include both air sealing at ceiling planes and insulation installation, producing combined benefits that neither measure achieves alone. The attic ventilation considerations affect proper ceiling insulation applications. Traditional attic ventilation moves outdoor air through attic spaces to prevent moisture accumulation and reduce summer heat buildup. This ventilation continues working effectively with R60 sealing, insulation provided that insulation installation doesn't block ventilation pathways. Proper baffles at eave vents maintain air passages beneath roof decks. Adequate ventilation area through soffit and ridge vents provides continued airflow. Attention to ventilation details during insulation work preserves the proper attic moisture and thermal conditions that prevent long-term building problems. The cost analysis for comprehensive ceiling insulation upgrades reveals favorable economics across most applications. Material costs for blown cellulose or fiberglass to achieve R60 levels typically run $0.50 to $1.20 per square foot of ceiling area. Installation labor, when performed professionally, adds $0.50 to $1.50 per square foot. Total installed costs thus range from $1 to $2.70 per square foot, or $1,500 to $6,750 for 1,500 square foot ceiling areas. Annual energy savings of $300 to $700 produce simple payback periods of 4 to 15 years, depending on specific circumstances. The interaction between ceiling insulation and other home improvements produces compounding benefits. Well-insulated ceilings allow heating equipment to operate less frequently at lower capacity, extending equipment lifespan and reducing electrical consumption for fans and controls. Reduced heating load can enable smaller equipment sizing for replacement installations, further reducing upfront costs. Reduced attic heat loss reduces temperature differentials that drive air infiltration throughout the envelope. The combined improvement approaches produce cumulative benefits beyond what individual measures achieve alone. Robert Cornfield, a building performance consultant in New Hampshire, has documented cases where ceiling insulation upgrades produce surprisingly large heating cost reductions in older homes. His tracked projects show that homes built before 1980 with minimal original ceiling insulation can achieve heating cost reductions of 35 to 50% through comprehensive ceiling insulation upgrades. The dramatic results occur because baseline conditions create heat loss magnitudes that sufficient insulation addition can transform substantially. The findings suggest that older homes with minimal insulation should prioritize ceiling insulation improvements to capture these exceptional returns available during initial upgrades. The moisture management considerations for ceiling insulation require attention during installation. Insulation installed on ceiling planes must not trap moisture that could compromise building components. Vapor barriers positioned appropriately based on climate conditions manage moisture flow properly. Attic ventilation maintains low relative humidity that prevents condensation on cold surfaces. Proper air sealing at ceiling planes prevents moist interior air from entering cold attic spaces where condensation could occur. Addressing these moisture considerations ensures that insulation improvements produce durable benefits without creating secondary problems. Now for the obstacles and limitations that affect ceiling insulation applications. First, the access limitations in some homes prevent straightforward insulation upgrades. Cathedral ceilings, vaulted ceilings, and finished attic spaces don't provide the open attic access that simple blown insulation applications require. These configurations may require more expensive dense pack installations, spray foam applications, or partial demolition for insulation access. The limitations increase costs and complexity substantially compared to straightforward attic applications. Second, the structural considerations affect some insulation approaches. Adding insulation weight to ceiling framing that was designed for minimal loads may create structural issues in some homes. Blown insulation of 12 to 18-inch depth loads ceilings at 1 to 3 pounds per square foot, typically within structural capacity. Spray foam applications add similar loads. Very deep applications or specialized materials may exceed structural capacity in some older homes, requiring professional evaluation before installation. Third, the existing insulation conditions affect project approaches. Homes with existing damaged or contaminated insulation may require removal before new insulation installation. Removal adds substantial cost and complexity compared to straightforward installations over existing insulation. Assessing existing conditions before project planning prevents cost surprises during installation work. Fourth, the HVAC equipment located in attic spaces creates installation challenges. Insulation around HVAC components must maintain appropriate clearances, accommodate service access, and avoid blocking ventilation pathways that equipment requires. Solutions include enclosing HVAC components within insulated cabinets, relocating equipment to conditioned spaces when feasible, or working around equipment carefully during insulation installation. The complications affect installation costs and may limit insulation depth around equipment. Fifth, the cold attic impacts on some building components require consideration. Piping in cold attic spaces becomes vulnerable to freezing without proper protection. Electrical equipment may need ventilation considerations. HVAC equipment designed for conditioned space installation may face issues in cold attics. Proper planning addresses these secondary considerations rather than focusing solely on pure insulation installation. Despite these considerations, ceiling insulation upgrades represent one of the most cost-effective home improvements available for most American homes. The combination of substantial energy savings, accessible installation methods, broad applicability, and reasonable costs makes these projects worth pursuing for nearly all homeowners with below-optimal existing insulation. The environmental implications of widespread ceiling insulation improvements extend beyond individual homeowner economics. If American homes with below-optimal ceiling insulation were brought to modern standards, national heating and cooling energy consumption would decrease by an estimated 5 to 8%. The corresponding carbon emission reductions represent meaningful contributions to broader environmental goals. Various utility programs and government incentives support ceiling insulation improvements, recognizing these broader benefits beyond individual homeowner savings. The health considerations for ceiling insulation work warrant attention. Fiberglass insulation can cause skin and respiratory irritation during installation, requiring appropriate protective equipment. Cellulose insulation contains fine particles that also warrant respiratory protection during installation. Professional installers follow appropriate safety protocols that amateur installers may not match. The health considerations favor professional installation for homeowners not prepared to follow appropriate safety practices rigorously. Margaret Chen, a utility energy efficiency program coordinator who has managed ceiling insulation improvements for over 3,000 low-income homeowners across California, has documented the transformation these improvements produce in participating households. The reduced heating and cooling costs typically improve affordability substantially for families struggling with energy costs. The improved indoor comfort enables better health outcomes for elderly and health-sensitive occupants who experience fewer temperature extremes within their homes. The program tracking demonstrates both economic and quality-of-life benefits that extend beyond pure energy savings. The building code evolution toward higher ceiling insulation requirements has gradually raised minimum standards over recent decades. Contemporary codes in most American climate zones require R38 to R49 ceiling insulation for new construction. Some jurisdictions have adopted higher minimums or offer incentives for exceeding minimum requirements. The gradual improvement trajectory suggests continued code evolution toward higher insulation standards, making current R60 installations likely aligned with future minimum requirements in many regions. The specific application in existing homes with cathedral ceilings presents particular challenges worth addressing. These spaces typically contain limited cavity depth that traditional insulation approaches can't achieve R60 levels. Solutions include spray foam applications that achieve higher R values per inch, additional insulation layers applied below existing ceilings that reduce ceiling heights, or supplementary insulation applied to roof exteriors during roof replacement. Each approach involves trade-offs between effectiveness, cost, and impact on interior spaces that homeowners must evaluate based on specific priorities. The seasonal performance characteristics of R60 ceiling insulation extend beyond winter heating benefits into summer cooling advantages that often surprise homeowners. During hot summer months, attic spaces routinely reach temperatures of 130 to 150 degrees as roof surfaces absorb solar radiation. That heat transfers downward through ceiling assemblies into conditioned living spaces, driving air conditioning demand substantially. R60 ceiling insulation reduces summer heat gain by 70 to 85%, compared to minimal insulation conditions. The cooling cost reductions often match or exceed the heating cost savings in climates with significant cooling loads. The combined annual energy impact across both heating and cooling seasons makes ceiling insulation upgrades particularly valuable in mixed climates with substantial demands in both directions. Patricia Donnelly, a whole home energy assessor operating across the Mid-Atlantic states, has documented comfort transformation patterns in homes receiving ceiling insulation upgrades. Her client tracking shows that second-story bedrooms that previously required supplementary cooling during summer nights returned to comfortable temperatures using normal central air conditioning following insulation upgrades. The ceiling surface temperature differences between uninsulated and R60 conditions reach 15 to 25 degrees during peak summer heat, eliminating the radiant discomfort that occupants experience beneath hot ceilings. The improved temperature uniformity throughout the upper floors represents a quality-of-life benefit that homeowners consistently report as equally valuable as the energy cost reductions. The regional climate variations affect insulation priorities and optimal R values across different American locations. Northern climate zones with long, cold winters benefit most from heating-focused insulation improvements, where every additional R value unit captures meaningful savings across the extended heating season. Southern climate zones with shorter, mild winters but extensive cooling demands benefit differently, with ceiling insulation reducing summer heat gain that drives substantial air conditioning costs. Mixed climates between these extremes benefit from balanced improvements serving both seasons. The R60 Target performs well across this range of conditions, though homeowners in very mild climates may find R49 sufficient, while those in extreme northern locations might consider R80 levels for maximum returns. The comparison between insulation improvements and other energy upgrade options illuminates why ceiling insulation earns its reputation as the premier starting point for comprehensive home efficiency projects. New, high-efficiency HVAC equipment typically costs $8,000 to $15,000, while reducing energy consumption by 15 to 25%. Window replacements cost $15,000 to $40,000 for whole home installations, while typically reducing energy consumption by 10 to 20%. Ceiling insulation upgrades at $3,000 to $6,000, producing 18 to 28% heating cost reductions dramatically outperform these alternatives on cost per percentage improvement metrics. The sequencing logic for comprehensive home efficiency improvements starts with ceiling insulation, proceeds through air sealing and wall insulation, then addresses windows and equipment in later phases. Harrison Velasquez, a weatherization contractor operating in upstate New York, has tracked homes where sequential improvements compound over time to produce dramatic cumulative energy reductions. His documented case studies show homes achieving 55 to 70% total heating cost reductions through comprehensive improvement sequences that start with ceiling insulation upgrades and progress through other measures over 3 to 5 years. The cumulative annual savings reach $1,500 to $3,000 for larger homes, with the initial ceiling insulation investment capturing the largest single-measure portion of those total savings. The documented sequences provide homeowners with practical roadmaps showing how phased improvements build toward dramatic long-term efficiency transformations, starting from accessible ceiling insulation projects. The installation timeline for professional ceiling insulation typically spans 1 to 3 days, depending on home size, existing conditions, and selected materials. The work proceeds with preparation activities, including covering air-sensitive surfaces, installing baffles at eave vents, and addressing air sealing needs at ceiling penetrations. The actual insulation installation moves efficiently once preparation is complete, with blown insulation application proceeding at rates of several hundred square feet per hour using proper equipment. The project completes with cleanup, inspection of air handler access and attic ventilation, and verification that installed insulation meets specified coverage and depth. The minimal disruption to homeowner daily activities makes ceiling insulation projects among the easiest home improvements to schedule and complete. The utility incentive programs supporting ceiling insulation improvements vary widely across regions, but often provide substantial rebates that reduce net homeowner costs. Federal tax credits under the Inflation Reduction Act provide 30% of material costs for qualifying insulation installations, capped at $200 annually. State and local utility programs add further incentives ranging from flat-rate rebates of $500 to $1,500 to performance-based incentives tied to documented energy savings. Low-income weatherization assistance programs provide fully subsidized installations for qualifying households through federal programs administered by state agencies. Researching available incentives before starting projects can reduce net costs by 30 to 60% for typical installations, dramatically improving already favorable payback economics. Gabrielle Moreau, a consumer finance specialist focused on residential energy investments, has analyzed return profiles across various home improvement options for middle-income American families. Her comparative financial analysis shows that ceiling insulation upgrades produce internal rates of return ranging from 12 to 25% when accounting for energy savings, incentives, and insulation operational lifespans. These returns substantially exceed typical investment alternatives available to most households, including stock market returns, bond yields, and certificate of deposit rates. The practical implication that she emphasizes involves treating ceiling insulation improvements as financial investments rather than discretionary spending, recognizing that the guaranteed returns through reduced energy costs represent reliable wealth. Building alongside the comfort and environmental benefits, the longevity advantages of properly installed ceiling insulation extend far beyond typical replacement cycles for other home systems. HVAC equipment typically requires replacement every 15 to 25 years. Water heaters need replacement every 10 to 15 years. Roofs need replacement every 20 to 40 years. Windows may need replacement every 25 to 40 years. Ceiling insulation properly installed performs reliably for 50 or more years without meaningful degradation. The single investment captures energy savings across multiple replacement cycles for shorter-lived equipment, accumulating lifetime savings that often reach $20,000 to $40,000 across full insulation operational lifespans. The durable nature of the benefits amplifies the already attractive economics substantially when viewed across proper time horizons. The common misconceptions preventing homeowners from pursuing ceiling insulation upgrades often involve underestimating existing conditions, overestimating project complexity, misunderstanding cost structures. Many homeowners assume their existing insulation performs adequately because the home feels reasonably comfortable, missing the substantial heat loss occurring despite apparent comfort. Many assume insulation upgrades require major construction disruption when most projects involve only attic access with no impact on living spaces. Many assume costs run substantially higher than actual market pricing, which contemporary competitive installation markets have driven to favorable levels. Addressing these misconceptions through practical information often motivates projects that homeowners would have pursued years earlier with better understanding. Consider what R60 ceiling insulation means for homes with baseline conditions below this standard. A modest investment in materials and either professional or self-performed installation reduces annual heating and cooling costs by hundreds of dollars. The savings continue across the insulation's expected 50-plus year operational lifespan. The comfort improvements throughout the home include warmer ceilings that eliminate the chill of cold interior surfaces, more stable indoor temperatures, and reduced cold drafts from attic air infiltration. The equipment operation becomes more efficient through reduced capacity demands. The environmental benefits accrue alongside the personal economic benefits. The approach works across most American homes with standard attic access, which represents the majority of the residential building stock. The skills required for simple blown insulation installation remain accessible to motivated homeowners. The tools and materials remain widely available and affordable. The knowledge requirements are modest and accessible through countless educational resources. The economic returns match or exceed any other simple home improvement opportunity. The long-term benefits accumulate reliably across decades of subsequent operation. The opportunity exists essentially for every American homeowner with below-optimal ceiling insulation, representing a substantial portion of the residential housing stock. The question isn't whether ceiling insulation upgrades provide benefits. The question is why more homeowners haven't already captured these substantial returns. The answer typically involves awareness, inertia, and misconceptions about cost, rather than any real obstacle to successful implementation. For most American homeowners with below-optimal ceiling insulation, pursuing improvements represents perhaps the highest return home improvement investment readily available, with benefits continuing reliably across decades of subsequent ownership.